And do you remember what was displacement current from the last lecture? Anybody wants to remind everybody else what displacement current was? Go ahead, please. Very good. You know, what we talked about is that we already know from Faraday's law that a changing magnetic flux produces an electric field. So what Maxwell said, Maxwell is another scientist, not the same as Faraday. What he said is that if changing magnetic flux can produce an electric field, why shouldn't the reverse be true? In other words, why shouldn't a changing electric flux produce a magnetic field? You know, so just from the symmetry idea. And what we talked about last time is that one situation in which you can think that the current, that the electric field is changing with time is when you are charging or discharging a capacitor, right? And so and it turns out that this idea that changing electric flux must produce a magnetic field is actually correct. And you can see this when you are charging or discharging a capacitor, for example. And this magnetic field that is induced, the changing electric flux produces a magnetic field. This induced magnetic field is due to a fictitious current that we called the displacement current, which you can think in your mind is flowing between the plates of a capacitor. Okay? And in fact, last time we showed that the displacement current, I sub d, was equal to epsilon 0 d phi sub E divided by dt, where phi sub E is the electric flux that is changing with time. This is the electric flux. Does anybody remember what is the definition of electric flux? You know this from Gauss's law also, because we were talking about electric flux even there. Who wants to tell me the definition of electric flux? You know, it's the total number of electric field lines that are going through an area. So it's going to be integral E dot dA, right? And the thing is, and if the electric field and the area vector are, if the electric field is constant in magnitude and electric field and area vector point in the same direction, in that special case, we can write the flux as E times A. If E magnitude is constant and the vector E and area vector point in the same direction. Do you remember this? Okay, we will get back to this in a minute, but let me first go over these concept tests. I just started it because Jim was trying to fix this clicker. So let's go over the first question. It says the figure below shows 3 circuits with identical batteries, inductors, and resistors. Rank the circuits according to the time for the current to reach 50% of its equilibrium value after the switches are closed. Smallest first. So you have 3 choices. Take your time. Talk to a person next to you. You have 1 minute to answer this question. Okay, if you remember, this question is related to an LR circuit, and the answer to this will depend upon what? The time constant of the circuit, right? Do you remember what was the time constant of an LR circuit? It depends upon the value of L, the inductance of the inductor, and it depends upon the value of R, the resistance of the resistor. So for an LR circuit, you know, the time constant that tells you how fast or slowly the current will decay depends upon, this is equal to L divided by R. Do you remember? Okay, so if that's the case, then it says, so if tau is large, if the time constant is large, what does that mean? That it takes a long time for the current to fall off, right? On the other hand, if this is small, that means it quickly falls off, right? Or quickly rises. If when you are increasing it or decreasing it, the changes will be quick, if the time constant is small. So in this case, can we figure out the time constant? Look at this. In the first circuit, tau in the first circuit, the time constant in the first circuit is L over R. For the second circuit, it is L divided by 2R, because though the two resistances are in series. In the third circuit, it's, this is tau 3. This is L divided by R over 2, because the equivalent resistance of two resistors in series is R over 2, right? Identical resistors, two identical resistors. So this is nothing but 2L over R. So you can see it's saying, rank the circuits according to the time the current reaches 50%. So in this case, you have to figure out what is the smallest time constant versus the largest, right? It says the smallest should come first. So current reaches 50% of its equivalent. So what is the smallest thing here? Isn't this the smallest? Right? So the ranking would be tau 2. The second smallest is tau 1, and then it will be tau 3. So the correct answer here will be 2, 1, and 3A. Right? So it looks like many people got the right answer. Is the idea clear how you figure this out? Any questions about this? Okay, let's look at the next question. It says the electric field between the plates of a capacitor points into the blackboard. If the capacitor is put in a circuit so that it discharges, the direction of the induced magnetic field between the plates of the capacitor will be which way? This question is related to displacement current that we talked about last time. The displacement current will be due to the fact that in this case, the capacitor plate is discharging. All right. So again, one of the other things that you need to think about is what is the relationship between the direction of the displacement current versus the direction of the real current in the wire. Does anybody remember from last lecture? What do you remember about the direction of the displacement current versus the direction of real current in a wire? Displacement current is a fictitious current that you can think of as flowing between the plates of a capacitor. So for example, if you have, say for example, a circuit like this, here is a switch, and the thing is, as soon as you close the switch, right, there is a current, there's a real current, which we said, okay, just for distinguishing it from the displacement current, we'll call it I sub C, right, conduction current in the wire. That current will start flowing like this. Another way to say this is that the electrons will start flowing from the negative towards the positive. So the electrons are flowing this way, electrons are accumulating here, positive charges are being left behind. This is the direction in which the electrons are flowing. We say that a current is flowing this way. So more positive charges come here, electrons go here. More and more positive charges come here, electrons go here. And you're building up an electric field. So you can see the electric field is increasing. What we said is that, actually I want to ask you, you think about this question before I actually discuss this. So the question is, this is the question. You have to think about what would be the direction of the induced magnetic field due to the displacement current. So in this case, you have to think about what is the direction of the induced magnetic field in this region due to the displacement current. First, you have to figure out the direction of the displacement current in this case, and you have to first think about what is the relation between real current and displacement current in order to figure this out. You have 1 minute. Talk to a person next to you. Okay, so one key thing to remember about this question, as we discussed last time, is that the displacement, the direction of displacement current is always such that it completes the loop. So in other words, it basically will be as though there was a real current flowing through the capacitor plates. So for example, in this case, if the real current is flowing like this, when you're charging a capacitor, which way will be the displacement current? You can think that there's a displacement current flowing between the plates of a capacitor, which is also in the same direction, so that the whole thing completes a loop. Sorry, Jim, did you want me to? Okay, perfect. Thanks, Jim. Here, is there any switch that I need to turn on? That's it? Okay, great, thanks. I think I should be okay. Does that make sense? So what we discussed last time is that displacement current will always complete the loop. In this case, you are charging the capacitor, right? So the displacement current will be in the same direction as the conduction current, and hence it will be this way, right? Now, what happens when the capacitor gets fully charged? When the capacitor gets fully charged, will there be any IC, any real current? No. IC goes to when the capacitor becomes fully charged. You know that IC will go to 0. In this case, is the electric field changing with time here? Is there any d phi E over dt anymore? Is the electric flux changing with time anymore between the plates? It's not, right? You see that once this thing is charged, the electric field is not changing. Electric field was only changing that the electrons were actually moving from this plate to this plate, and more charges were accumulating there. Only then was the electric field changing between the plates. Once the capacitor gets charged, electric field between the plates stays constant. Electric flux here is not changing with time. In this case, what happens to the displacement current? Even that will go to 0, right? Now what happens is, suppose I want to discharge this plate, right? So the thing is that the real current and displacement current, they both go to 0 after the capacitor becomes fully charged. So the only time the real current and displacement current flows is when the electric flux is changing with time between the plates of the capacitors, right? And when will that happen? Either when you're charging the capacitor plate or when you are discharging it. Now let's think about discharging, because this question is about discharging. Now suppose I discharge, how can I suppose I take the battery out. Basically what I'm saying is that suppose that we take the battery out of this circuit. If we take the battery out of this circuit, what happens? Now will the capacitor act like a battery? Of course, there's always some small bit of resistance here in the circuit, so don't worry about, it's not that there's no resistance in the circuit, there is always some resistance even in the wire, even if you don't put it explicitly. Which way will be the real current flowing in the wire as the capacitor discharges now? Tell me. Based upon what you learned 2 months ago, which way will be the the real current in this wire as the capacitor is discharging? Just think about it. As the capacitor is discharging, the negative charges from this plate now see, oh, there is this path, we can go back and we can combine with the positive charges. They hate each other anyway, they want to combine with the positive ones, and now there is no battery that is pushing them in that direction. So now what they'll do is these negative charges will go and combine with the positive charges, and that another way to say it is that there will be a discharge current flowing this way. Wouldn't this be the discharge current? Is everybody seeing this is the discharge current? Why? Because the electrons are going and combining in this fashion when the capacitor is discharging, and the capacitor is responsible for passing the current in the circuit, right? Which way should be the displacement current in this case? Remember, displacement current always completes the loop, right? So the thing is, if this is the direction of the real current, then the displacement current in this case should be flowing in this direction, so that it's as though, and remember, you have to think about displacement current as though it was flowing between the two plates of the capacitor in this full region, in this whole fat region like this, right? So if that's the case, let's try to answer this question, because this is just put in a slightly different perspective. So this is a top view, so it's not any different from this picture, it's exactly the same, just that you are being shown a picture where the capacitor plates are pointing that way. So it says the electric field between the plates of a capacitor points into the blackboard. By the way, which way will the electric field be pointing? Do you notice that the electric field will always be pointing from the positive to the negative plate? Is everybody convinced that electric field always points from positive of the positive plate of the capacitor to the negative? But when the capacitor is discharging, the discharge current is flowing opposite to the direction of electric field. Do you see that? So in this case, when you are told electric field between the plates of the capacitor points into the blackboard, you know, this is the electric field. Which way do you think is the, suppose these are the plates of the capacitor, you can see that. This is the electric field going into the board, you know, so maybe this is the positive plate, this is the negative plate, and the electric field is going this way. Which way will the displacement current be in this case? Will it be coming out at you? Wouldn't it? Yeah, because see, if the electric field is this way, displacement current is that way. So the displacement current will be dots. And now that you know the displacement current, can you figure out which way will be the magnetic field due to the displacement current? It's always the right hand rule. Put your thumb in the direction of current, your fingers will curl around in the direction of magnetic field due to that current. So this induced magnetic field between the plates of the capacitor will be, you know, given by putting your fingers in the direction of current which is coming out at you, and you can see that your fingers curl like this in the counterclockwise direction. Is everybody seeing that? So the correct answer here is counterclockwise D. So what I'm saying is that the magnetic field due to this current will be this way. I mean, there are too many things in this picture, but I hope that you can see that these arrows that I'm drawing are the magnetic field lines. These crosses that I have drawn is this electric field. Electric field is pointing from this plate, positive plate, to the negative plate of the capacitor. In this case, the plates are like this, and so it's pointing this way. Does that make sense? Is there any question about this? And so the displacement current during discharge is opposite to the direction of electric field that is changing with time. So the displacement current will be pointing towards us. If the displacement current is pointing towards us, we can figure out the direction of the induced magnetic field. Any questions, folks? All right, let's look at one more question before we move on. It says, the quantity b square over mu 0 has the unit of, there are 5 choices given to you, 1 minute to answer this question, talk to a person next to you. Okay, the correct answer here should be joules per meter cubed, because this is the unit of energy density. If you remember, the energy stored in the magnetic field, if you remember, we had discussed what is the energy stored in the magnetic field of an inductor, and what we found was that it was b square divided by 2 mu 0. Remember? And I said that this is actually a general result for the energy stored in the magnetic field. Today we are going to talk about electromagnetic waves later, and you will see that even in the electromagnetic wave, which consists of a changing electric field and changing magnetic field, the energy that is stored in the magnetic field per unit volume is still given by this. This is the energy density, energy per unit volume, which is called energy density. So its unit is joules per meter cubed, right? Any questions about this? Anybody? Okay, then let's move on. And the first thing that I'm going to talk about today will be an example for this displacement current thing. So let's try to figure out in a particular situation what would be the magnetic field produced, say, at some distance away. So let's take a problem in which the radius of the capacitor plate, let's say, is 5 centimeter. Okay? You are told that at one given instant, you are given at a particular instant, the real current in the circuit is, let's say, half an amp. You are asked to find the direction of displacement current we are already seeing during discharge, right? Let's say we were told, find the magnitude of the magnetic field that is produced at a distance little r, let's call it r1, which is 1 centimeter from the center of this capacitor plate, and at a distance r2, which is at a distance of, let's say, 6 centimeters. So the question is, what is B, magnitude? Magnetic field induced magnitude. What is B, induced magnitude? Is the question clear to everybody? A capacitor is discharging, all right? At a given instant, you are told that the real current that is flowing in that wire is half an amp. You are also told that the radius of the capacitor plates is 5 centimeter. It's a circular plate. And you're asked, what is the induced magnetic field due to the displacement current at r equal to 1 centimeter and r is equal to 6 centimeter from the center of the capacitor plate? Can you answer this question? What principle will we use? Again, we have discussed this last time. Tell me. Anybody? The principle that we will use looks awfully like Ampere's law. This is called Maxwell's law of induction. Do you remember what Maxwell's law of induction was? Anybody remembers? Go ahead, folks. I think you remember. What was Maxwell's law of induction? Maxwell's law of induction basically says that integral over any closed loop of B dot dl is equal to mu 0 times ID enclosed. Doesn't this, isn't this deja vu? I mean, doesn't this remind you of Ampere's law? In fact, it is actually exactly like Ampere's law. Just compare this with Ampere's law. That the Ampere's law said integral B dot dl was equal to mu 0 times the real current enclosed, IC enclosed. And here we are saying, well, if you're dealing with displacement current, which is a fictitious current, then this is the, if you like, you can call it the B induced. This is the induced magnetic field due to the displacement current. This is called Maxwell's law of induction, as we learned last time, right? So again, in order to find the magnetic field here, what kind of loop should we choose? Can you think of, let's do it one by one. We have been given two-part question. First, we have to find it at R1, let's say, then at R2. So at R1, what kind of loop, Amperian loop, should we be choosing? Because look, integral B dot dl should be mu 0 times ID enclosed. We have to choose a closed loop. This closed loop, remember, we used to call it Amperian loop. And even if we are using displacement current, we can still call it Amperian loop. So what kind of loop should we be choosing there? Remember, we have to choose a loop in such a way that we can say that the magnetic field magnitude is constant everywhere on that loop, so that we can pull this B out of this integral, right? So that we don't have to do any complicated integrals to find the B. So shouldn't the loop that suppose we have to find the magnetic field here, shouldn't we choose a loop which is a circle with this radius R1 with the center at the center of the capacitor plate? Wouldn't that be a good loop to choose? Because there, would you say that magnetic field induced due to this displacement current, this fictitious displacement current through the plates of the capacitor, wouldn't you say that the magnetic field magnitude is constant everywhere on this loop? Just from the symmetry, it has to be constant. And if it's constant, we can pull this B induced out, and then By the way, the direction of the dl, you can move in the direction, dl is the length vector along this loop, and you can see that you can move in the direction of the magnetic field because the magnetic field lines are forming closed loop. So the angle between these two will be 0. Do you see what I'm saying? Because B dot dl is really magnitude of B, magnitude of dl times cosine theta, but I'm saying in this case it's cosine 0, which is 1. So all we have is B induced gets pulled out because it's constant on the loop that we chose. Integral dl is nothing but, is it 2 pi r1? Integral dl? Isn't it? Over that closed loop that we chose. And that should be equal to mu 0 times id enclosed. Okay, and that means B induced should be equal to mu 0 id enclosed divided by 2 pi r1. This is for case 1. For r1, which is less than the radius of the plate. The only thing is, do we know id enclosed? How do you figure out how much is the displacement current that is enclosed? Is all of the displacement current enclosed here in this loop here that you chose? Look, this is the loop you have chosen because you are asked to find the magnetic field here. Is all of the displacement current enclosed there? No, because the displacement current should be thought of as flowing through the whole, between all the plates of the capacitor. So the thing is, not all of the displacement current is enclosed here. How can we figure out if the current is flowing uniformly? First of all, will you agree with me that IC should be equal to total ID? That's always true. I proved to you last time. If you look at your notes, you will see that IC is always equal to ID, total IC. So that means the real current flowing in this wire should be thought of as the total current flowing through the whole capacitor plate. So if IC is equal to ID, we need to find what is IC, ID enclosed. Can I say this? Is this fair to say that ID divided by the total area of the capacitor plate, this is the current density, should be equal to ID enclosed divided by pi times R1 square. This is again the current density. Both of them give me current density. One is in terms of the total current divided by the total area of the plates. The other one is in terms of ID enclosed divided by the area of the loop that you have chosen. Is that making sense? And if that's really correct, tell me if you agree with that. And if you agree with that, then you can see that ID enclosed should be equal to pi and pi get cancelled. It will be equal to ID times R1 square divided by R square. Right? But what is ID, folks? Is ID equal to IC? Yes, that is something that I proved to you last time. If you check your notes, you will see I proved that displacement current is always equal to the real current in the wire. So when you are charging or discharging a capacitor plate, you can think that there is a fictitious current, this displacement current, which is given by this formula here, which is always equal to the real current IC. Okay, if that's the case, can we plug it here? Yeah, we can plug it here and we can see that let me just what you can see is that B induced then turns out to be equal to mu 0, and instead of ID enclosed, I'm going to use this, which is going to be ID is equal to IC times R1 square divided by R square divided by this thing 2 pi R I always had, 2 pi R1. Notice that one of these R1s get cancelled here, so I get B induced is equal to mu 0 divided by 2 pi R square times IC times R1. I'll leave it for you to plug the numbers. At this point, it's just plugging numbers. IC is given to us to be half ampere there. R1 is given to us to be what? 1 centimeter. And capital R, the radius of the plate, is given to us to be 5 centimeter. All you have to do is plug in and you have the answer, right? Do you notice one thing, that B, if I asked you instead to make a plot of B induced, how will you plot it? B induced as a function of R from the center of the, this is the center of the capacitor plate. Tell me, B induced as a function of R, what will it look like? When R1 is equal to 0, B is 0. Do you see it's increase? All of this is constant, right? If IC is constant and R plate of the capacitor has a fixed radius, then B is proportional to R. So it actually increases like this, all the way till you get to which point? R is equal to capital R. Let's try to figure out the second part of the problem. Second part is going to be trivial, really easy. So second part asks us to find the magnetic field here. What kind of Amperian loop should we choose? Should we again choose a circle going through here? Shouldn't we choose this? Isn't that true? Let's call this distance R2 here. So for case 2, so case 2 is, R2 is greater than the radius of the capacitor plate. In this case, again, we can use integral B dl, and again the angle between the two is cosine 0 over the closed circle will be equal to mu 0 ID enclosed. B gets pulled out because it's constant. Integral dl gives me 2 pi R2, and that should be equal to mu 0. What is ID enclosed this time, folks? Can anybody tell me what is ID enclosed if you're choosing a point which is at a distance of 6 centimeters from the center of the capacitor plate when the radius of the capacitor plate is 5 centimeters? What is it, folks? Oh, all of you should be able to answer it. Go ahead, please. Very good. It should be the total current. ID enclosed in this case is ID. Because if you're looking at the magnetic field at a point which has a radius larger than the radius of the plate, all the current that is flowing through the capacitor plate, all this fictitious current is enclosed. So ID enclosed in this case is ID. So then the magnitude of B is mu 0 ID divided by 2 pi R2. That's it. But remember, ID is equal to IC, isn't it? ID is always equal to IC in magnitude. So the thing is, B is equal to mu 0 I C divided by 2 pi R2. So in this case, do you see that B is, all of this is constant, for example? Then do you see that B is proportional to 1 over R2? So outside, if you like, let me put that thing on this plot also. The thing falls off, the magnetic field falls off. B as proportional to 1 over R. And here B is proportional to R. This is B is proportional to R here, B is proportional to R. And here B is proportional to 1 over R. All this junk is constant. This is outside. If you ask me what is the magnetic field induced due to this displacement current outside the plates of the capacitor, it will be given by this formula. I'm not going to plug in the numbers. R2 is given to be 6 centimeters. IC is half an amp. You can plug in the number and you have the answer. Any questions, folks? Anybody? Okay, then we are going to move on, and now we are going to talk about electromagnetic waves. Whether you realize it or not, we have actually accomplished a lot in this course, because in fact you should know, at this point everything that there is to know in electricity and magnetism. So for example, what are the things that you know now? You have learned lots of different equations, and as I said to you last time, that this particular equation, this equation integral B dot dl is equal to mu 0 times ID enclosed. This is called Maxwell's law of induction. This is the last equation that we needed to understand everything about classical electricity and magnetism, everything. Because we already know a lot, and so no matter how complicated your electronic circuit is, if you're trying to figure out anything electrical or magnetic in that, using these equations, you ought to be able to infer every single thing. So let's see what we already know. And all these equations here are called Maxwell's equations to honor Maxwell for his last contribution that put everything together, that made people understand. So one of the things that we have learned is Gauss's law of electricity. Gauss's law of electricity says this: integral E dot dA is equal to Q enclosed over epsilon 0. This is Gauss's law of electricity. Another one is Gauss's law of magnetism. Do you remember what was Gauss's law of magnetism? Anybody? What should be integral B dot dA? What should be the integral over any closed surface of the magnetic flux? It's 0. Why? Because you can never have just north pole or south pole. Even if you just enclose an electron in a loop, not in a loop but in a closed surface, an electron itself has a north pole and a south pole. So you can never have just an isolated charge isolated pole like you would have isolated charges. Okay? So this is always 0. This is called Gauss's law of magnetism. This is called Gauss's law of electricity. By the way, I'm not going to write down Coulomb's law separately, because remember, for electrostatics, Gauss's law and Coulomb's law are equivalent. And this is the more beautiful way of writing things. Okay, then what else did we learn? We learned Faraday's law. Faraday's law says this. It says that integral E dot dl was equal to minus d phi b over dt. So that means this is the induced electric field. Remember, we had, you can call it V induced if you like. V induced could be written in terms of induced electric field. Remember, we said induced electric field will form closed circles. Do you remember that? So they are related. Okay, and what is the last thing? We already know what? Ampere's law. And Ampere's law says integral B dot dl over any closed loop is equal to mu 0 times the real current enclosed. This is Ampere's law. But just now we learned Maxwell's law of induction last time. When will we start using Maxwell's law of induction? When this B is not due to a real current, but it's due to displacement current. So, maybe we'll combine the two formulas together and we'll say this is plus mu 0 times ID enclosed. Now, which one you will use, whether you will say integral B dot dl is equal to mu 0 times IC enclosed, or whether you will say integral B dot dl is equal to mu 0 times ID enclosed, depends upon whether the magnetic field that you're talking about is due to real current or displacement current. Do you see I've combined two different formulas together? So this formula is called Ampere-Maxwell law. This thing here is called Faraday's law. Okay, and these four things together are called Maxwell's equations. All of these four equations together are called Maxwell's equations. In addition to this, there are only two things you need to know to be able to do anything in electricity and magnetism, and those equations are this. F of E, the electric force on a charged particle, is Q times E, and F of B, magnetic force on a charged particle, is Q V cross B. Believe it or not, you don't need anything else. With these equations, you ought to be able to infer everything that we know about how light works, how circuits work, no matter how complicated, how sophisticated they are, everything. Now, using these equations, one of the great things about Maxwell's contribution, as soon as we figured out this thing about displacement current, he was able to show that light, as we know it, this light is an electromagnetic wave. What is an electromagnetic wave? An electromagnetic wave is a wave that has a changing electric field, an electric field that is sinusoidal, as you can see here. It's changing with time, and it has a magnetic field that is changing with time. And it turns out that in an electromagnetic wave, such as light wave, you have, it doesn't have any mass. There is nothing that has mass in light. Okay, it's not like the massive particles like we know, things in the periodic table that have masses. Light doesn't have anything that is there in this periodic table. Okay? It only consists of changing electric field and a changing magnetic field, and it turns out that in a light wave, electric field and magnetic field are always perpendicular to each other. Do you see? So for example, if the electric field is oscillating, has its oscillation in the y direction, then let's say the magnetic field will be oscillating in the z direction, which is coming out at you, and electric field and magnetic field are also perpendicular to the direction in which the electromagnetic wave is moving. So for a light that's coming right at me like this, say the electric field could be oscillating this way, the magnetic field could be perpendicular to that like that, right? And then there's one direction like this, that is the direction in which light is heading. So the point is, in all electromagnetic waves, this is true. The direction of propagation, the direction of electric field, and the direction of magnetic field are all perpendicular to each other. Now, there's something very bizarre about electromagnetic waves. What is so bizarre? Such as light. Do you know that light can come from the sun all the way to Earth? Do you know what is there most of the way between sun and Earth? Vacuum. There's nothing. Vacuum means there's absolutely no matter, nothing. In this periodic table, there's nothing. So it's empty space, nothing. If there's nothing, how is it that light is able to come all the way from the sun to Earth? Because do you remember that waves carry energy with them? Right? Remember from physics 1, I didn't teach you, but the thing is, if you remember from physics 1, waves carry energy with them. And how do waves usually carry energy? So for example, right now I'm talking and sound waves are actually arriving at your ears and they are jiggling your eardrums and you're actually able to decipher what I'm saying. How does it work? Basically what's happening is that, my vocal cords are vibrating, they are vibrating the air close to it, and then the next air, then the next air. It's not that the air close to me is moving close to you, but each of them pushes, vibrates and pushes the air next to it and next to it, etc. So in other words, the wave travels from this disturbance in the medium, right? Because one molecule in the medium pushes the other molecule, in fact, it turns out that in solids, sound will travel even better, faster than in air. In fact, if you remember, like speed of sound in solids is faster than speed of sound in air, or speed of sound in liquid will be somewhere in between these two. Because the particles of the medium convey the information much easier in the case of solids. Okay? But in electromagnetic wave, we are saying you don't need any medium, there's nothing. And still light is able to come all the way from sun to Earth. How is that possible? Because, if suppose you and I went to moon, on moon there is no air, nothing, there's no medium. It's vacuum on moon. You would be standing there and I could be standing here. If I speak, you will hear nothing. Nothing. Remember, in space no one can hear you scream, and it's true. It's true because the thing is, if there's no medium for propagation of the sound waves, it's not going to go. So how is it that electromagnetic waves can propagate, please? Well, light can act as a particle, but here we are not going to talk about any quantum mechanical nature of light, because those things, you're right, that can actually explain certain kinds of phenomena, such as photoelectric effect and things. But that's not the phenomena that will be responsible for why light is able to travel through vacuum. But you're right, for some certain things, quantum mechanics, if you think of light as consisting of photons, you can actually show certain things. But that's not important for anything we are going to talk about in this class here. So why is it possible? It turns out it is possible because of Faraday's law and this Ampere-Maxwell's law. Why? Because if light consists of changing electric field, look, electric field is sinusoidal, it's oscillating with time. The magnetic field is oscillating with time. Does the changing electric field produce a magnetic field? And does the changing magnetic field produce, look, changing electric field, we said here, will produce a magnetic field. The changing magnetic flux will produce an electric field. By the way, remember, displacement current is nothing but changing, it's related to changing electric flux. So from Maxwell's equations, we can see that since changing electric flux produces a magnetic field and changing magnetic flux produces an electric field, in an electromagnetic wave, the reason the wave is able to propagate without any medium, nothing is there, and still it's able to come unimpeded, is because of the fact that electric field all the time is producing magnetic field. This changing electric field is producing magnetic field, and the magnetic field is producing the electric field, so that the two things sustain each other as the wave moves ahead. Does that make sense? And this was one of Maxwell's crowning glory, like the fact that he was able to show, he was able to add his contribution that says that changing electric field will produce a magnetic field, and people were able to understand light that they had been trying to understand for a long time. Everything just, the light bulb just went off, and everybody said, oh, makes perfect sense. And all the things that they tried to infer once they understood this, Faraday's law and Maxwell-Ampere's law, light, the study of light became totally clear to them. Now, when scientists talk about light, they don't just talk about visible light. Do you know what are the other kinds of electromagnetic waves there are? Because light, the word light is often used not just for visible light, but for all different kinds of electromagnetic waves. Can you tell me, like, what are the other different kinds of electromagnetic waves? Very good. Infrared is one kind of electromagnetic wave. What else? For example, your TV remote control, the way it communicates with your TV is through infrared waves. It sends out infrared waves. In fact, our bodies are constantly emitting, believe it or not, our bodies are constantly emitting infrared waves. Only when something is really, really hot, like a tungsten filament, does it give out visible light. But all objects are constantly radiating and absorbing radiation, and we do infrared. Go ahead, please. Yeah, ultraviolet. In fact, sunlight not only consists of visible light, there's a lot of ultraviolet too. In fact, that is the reason why you're told to put sunscreen, because ultraviolet lights have high enough energy that they can knock off electrons from your skin, and it can be dangerous. It can cause cancer and things. What other kinds of electromagnetic waves or light can you think of? Radio waves. Believe it or not, radio waves. The radios that you listen to in your car is an electromagnetic wave, which you can call light wave if you like. Like in a general scientific language, light wave means all of the electromagnetic waves. What else? Microwave is an electromagnetic wave. What else? X-rays, gamma rays, all of these things are electromagnetic waves. If all of these things are electromagnetic waves or light waves, what is the difference between them? And what is the similarity between them? Do you know what is similar about them? They all travel at speed of light in vacuum. So all of these things will travel at speed of light in vacuum. So all electromagnetic waves or light waves will travel at speed of light in vacuum. When I write EM wave, I mean electromagnetic waves. All travel at speed of light, at the same speed in vacuum. Do you know what it is? What? And the speed of light in vacuum is 3 times 10 to the power 8 meters per second. Or also, from your waves class in physics 1, can anybody remember what is the relation between speed, the frequency, and the wavelength of a wave? By the way, do you know the meaning of wavelength? Tell me what would be the wavelength in this last picture. What's the wavelength? Wavelength is the distance between two points which are in the same phase, right? For example, 2 peaks or 2 crests, or for example, the distance between this and this will be the wavelength of light, this particular light, right? Or you can choose, say, for example, the distance between these two. Notice something else about light. Light is very interesting. The maximum of the electric field and the maximum of the magnetic field occur exactly at the same place. The zero of the magnetic field and electric field occur at the same place. Another way to say this is the electric and magnetic fields are in phase. Yeah, that's a good language to use, isn't it? Electric and magnetic field are in phase in an electromagnetic wave or light wave. So what is C? Tell me. What is the relationship between this thing called wavelength, which is, say, the distance between 2 peaks or 2 points which are in the same phase, 2 adjacent points in the same phase, and the frequency? What is frequency? It's 1 over period, right? That means frequency means how many cycles, how many times does the thing come back, go back and forth How many cycles does it make every second? That's frequency, right? Tell me the relation between speed, wavelength, and frequency, because if you're taking a physics class, these are so fundamental, you cannot forget this even 10 years from now. What is the relation between speed of the wave, frequency, and wavelength, please? Very good. The speed of a wave is equal to the frequency times the wavelength. This is the frequency. That means number of cycles per second, and this is the wavelength, which is, as I said, this thing, the distance between two peaks. Okay? So then what is different about these different electromagnetic waves? Can you guess what's different? Go ahead, please. Huh? Yeah, they do have different energies. And why do they have different energies? Because they have different frequencies. It turns out that different electromagnetic waves all have different frequencies. And if they have different frequencies, will they also have different wavelengths if their speeds are all the same in vacuum? So higher will be the frequency, lower will be the wavelength, such that the product of the two is always equal to the speed of light in vacuum. Isn't that true? Do you see that? And it is true. What she said is true too. Later on what you will see is that higher is the frequency of a wave, more is its energy. So for example, in this spectrum of electromagnetic waves that I'm showing you, these here, radio waves are right here. AM waves have a lower frequency than FM waves. So AM is very low, FM is higher than that, microwaves are higher frequency than that, infrared is higher than that. This little region here is the visible light that we have blown up here. So this little region has been blown up to show you all the colors, and red light has a lower frequency than the violet light. Then you have ultraviolet light, even higher frequency, X-rays even higher frequency, and gamma rays even higher frequency. By the way, there is no limit to how high you can go in frequency. There is no limit on how low you can go in frequency. So electromagnetic waves can have as low frequency as you can imagine and as high frequency as you can imagine. Okay? There's no limit. But the thing is, as the frequency, so radio waves, do you think they will have a very high wavelength or short wavelength? High, right? If they have low frequency or low energy, they will have high wavelength. On the other hand, gamma rays is the name given to the highest frequency electromagnetic waves. Everything above a certain value, let's say all the things that have frequency higher than 10 to the power 20 hertz will be called gamma rays. So if gamma rays are very high frequency, they must have very low wavelength. So the distance between two peaks of the electric field, two things in the same phase, two adjacent things in the same phase, is very, very small for gamma ray. All the things in the middle will be somewhere in the middle. So do you see that 10 to the power 4, this is the hertz is the frequency over here. FM radio has a frequency of 10 to the power 8 hertz. Did you guys know this? You always listen to the, radio, so you probably know that FM radio has a frequency of 10 to the power 8 hertz, right? As you keep going. Visible light, what is the frequency of visible light? It is between 4 times 10 power 14 hertz to 7.9 times 10 power 14 hertz. That's what we choose to call visible light, because that is the kind of thing that we can see. All the rest of the electromagnetic waves you cannot detect with your with your eyes. So infrared waves, we are saying that you're constantly emitting infrared waves. When you turn on the remote of your TV, you are somehow transmitting a signal, but you can't see it. But it's still an electromagnetic wave that travels at speed of light in vacuum. Infrared will have a smaller frequency than visible light, so it will have a higher wavelength because the product of the two is constant. Does that make sense? Okay, now the other thing that I wanted to say is that since electric field and magnetic field of an electromagnetic wave are in phase, and you can see electric field and magnetic field are sinusoidal, let's write an equation for the electric field of an electromagnetic wave and the magnetic field of an electromagnetic wave. So suppose I choose to call the electric field of an electromagnetic wave, and let's say that it's pointing in the y direction, so I say E is equal to some maximum times sine kx minus omega t. By the way, you know what k is? I think you learned it in physics 1. K is 2 pi divided by lambda. It's called the wave number or wave vector. And do you know what omega is? Omega is 2 pi times the frequency. So let's say this is the electric field of the electromagnetic wave in the j hat direction. Then I can write the magnetic field of the electromagnetic wave as the maximum value B sub m. Should it be also sine or cosine? Tell me. It should be sine. Do you see they are in phase completely? Where the electric field is maximum, magnetic field is maximum too. So if one of them is sine, the other one will be sine also. But if this is in the y direction and if this is in the z direction, let's call it k hat, in the k hat direction. Now experiments show this. Experiments show something very interesting. Experiments show that you don't need to know the magnitude of both electric and magnetic field because they are related to each other. So it turns out that the magnitude of electric field is always equal to the speed of light times the magnitude of magnetic field. So in other words, if you like, the maximum value of electric field will be equal to c times the maximum value of magnetic field. But this relation will hold at any point. So if you tell me what is at this thing, what is the electric field, I will be able to tell you what is the magnetic field at exactly the same location, because by using just this relation, E is equal to C times B. Does that make sense? Also, you can show that the speed of light is related to two fundamental constants that we talked about in electricity and in magnetism. What is one fundamental constant that sticks in your mind from electricity? That we only seem to use a lot in electricity. And there was another fundamental constant that we only seem to use a lot in magnetism. What were they? Anybody? Folks, what were the fundamental constants that we kept talking about over and over again in electricity and over again in magnetism? Epsilon 0 in electricity and mu 0 in magnetism. Do you remember that? And what you can show that the speed of light is related to these things. It turns out that speed of light in vacuum is 1 over square root of epsilon 0 times mu 0. So speed of light in vacuum is related to those things. Okay, now we are going to talk about how to figure out how much energy is being carried by an electromagnetic wave. In order to figure out how much energy an electromagnetic wave is carrying, since all waves carry energy, we are going to talk about something called the pointing vector. What is pointing vector? Pointing vector S is defined as E cross B divided by mu 0. And what is special about pointing vector? I'll tell you in a minute. One thing that is for sure is that the direction of pointing vector is always going to be in the direction of wave propagation, electromagnetic wave propagation. So EM wave travels in the direction of the pointing vector. Okay, let's think about the magnitude of pointing vector. By the way, so what will be E cross B here? Can you do E cross B here and check this out for yourself? This is the right hand cross product rule, right? Put your fingers in the electric field, cross it in the direction of magnetic field, which is pointing in the z direction coming out at you. Do you see your thumb points that way? And that is indeed the direction of propagation of the wave. So you can see pointing vector will give you the direction of propagation of electromagnetic waves. Now what about the magnitude of pointing vector? Let's think about the magnitude. let's think about what the magnitude of this Poynting vector means. First of all, its magnitude will be E times B times sine of angle between B and E. What is the sine of angle between electric field and magnetic field? 90, right? Because magnetic field and electric field are always perpendicular to each other in an electromagnetic wave. So this is sine 90 divided by mu 0. And sine 90 is obviously 1, right? So if you like, by the way, can I write B in terms of E also? Or E in terms of B also? Yeah, we can make use of this relation. E is equal to C times B. Let's just do it, just for fun of it. So what you can see is that the magnitude of Poynting vector will be E. Okay, instead of E, I'm going to write C times B sine 90 is 1 divided by mu 0. So that means the magnitude of Poynting vector is C over mu 0 times B squared. And if you like, B squared can be written like this. Can I write B squared as Bn squared sine squared kx minus omega t? I can. So this thing I ought to be able to write like this. C over mu 0 B maximum square times sine square kx minus omega t. Suppose I ask you this question. How much is the average value of Poynting vector? What would you tell me? Do you know how to find the time average of sine square? Sine square. What is the time average value of sine square kx minus omega t? That's the question I'm asking you. Anybody wants to tell me? So the question I have for you is, what is the time average value of Poynting vector? Because it's a very important thing. It's called the intensity of the electromagnetic wave. So I, which is called intensity of electromagnetic wave, is really the time average value of S, the magnitude of S. Do you know the meaning of intensity? Intensity is the energy that the electromagnetic wave is carrying per unit area, per unit time. You know, can we give another name to energy per unit time? Tell me. Power, very good. So we can give it a name, power per unit area. So another way to define intensity would be to say intensity is power per unit area. How much energy of the electromagnetic wave is falling in a unit area, 1 meter square, per unit time, per second, right? That's the Poynting. So how do I find the, tell me, anybody knows how to find the average value? We need to average this whole thing out, time average of this thing. How do I average this whole thing out? I think you should be able to say this from math class. Everybody should be able to say what is the average, time average value of sine square function. Let's plot sine square. You know, if you plot a sine square function, I don't care it's kx minus omega t or what, but suppose I'm plotting it as a function of time. Do you know what will happen? What is the minimum value of sine? Minimum value of sine would be, sine square will be 0, and the maximum value of sine square will be 1. Do you see that it will be between 0 and 1? So basically this value will oscillate between 0 and 1. You know, the maximum value here is 1 and the minimum value is 0. Can you see what its average value will be? Can you make a guess? Half. Does that seem reasonable? Half will be the average value? Yeah. So its average value is half. So basically then the average value of the Poynting vector, which is related to intensity, will be this. So intensity is defined as average value. This sign here on the top tells me it's average, time average value. And so intensity then becomes, look over there, it's C divided by mu 0 times Bm square, and instead of sine square, I'm going to write half. Is this making sense, folks? Yeah? Okay. So this is the intensity. I suppose you were given a problem in the exam in which you were not given the maximum value of the magnetic field, you were given the maximum value of the electric field. Will you still be able to find the intensity or not? Yes or no? Why? Because E sub m is equal to C times B sub m. So all you need to know is either the maximum value of electric field or the maximum value of magnetic field, and you're all set. You will be able to find the intensity. The other things are constants anyway, right? The speed of light and the permeability constant, mu0 of free space. Any questions about this? Okay, now let's see, how much do you think is the energy that is being carried by the electric field of an electromagnetic wave versus the magnetic field of a electromagnetic wave? Any guesses? Which one do you think carries more energy, electric field or magnetic field? Any guesses? I haven't taught you, but we'll see it in a minute. Make a guess. Huh? Okay, that's a good guess. Any other guess? It turns out that both of them carry the same amount of energy. So in other words, half the energy of an electromagnetic wave is carried by electric field and half is carried by magnetic field. Let's try energy per unit volume. The easiest way to talk about it is how much is the energy carried in a unit volume, right? So let's think about it. So if you remember, so energy per unit volume in electric field of an electromagnetic wave, let's give it a name, u sub E, this is little u sub E, this will be equal to half epsilon 0 times the electric field square. Right? Similarly, what would be the energy per unit volume in the magnetic field of an electromagnetic wave? U sub m will be equal to half v square over mu 0. Is that true? Is everybody with me? Are they equal? Let's see. Let's see if they are equal or not. Let me write this in terms of electric field. How can I write B in terms of E? Anybody wants to tell me how to write B in terms of E? Do you remember here this? Using this, can I write B is equal to E over C? I can, right? So let's write B is equal to E over C. So this becomes half E square over C square times mu 0. But hey folks, we also talked about what is the relationship between speed of light and epsilon 0 and mu 0. Remember this? C is equal to 1 over square root epsilon 0 times mu 0. If that's the case, what will be C square? Is C square equal to 1 over epsilon 0 mu 0? Isn't it? So if that's the case, what will be C square times mu 0? Can I take mu 0 here? Can I take this mu 0 from here and put it here? So if you see, what I have here is nothing but half epsilon 0 E square. And so this is exactly equal to this. That means the energy per unit volume in electric field is exactly equal to the energy per unit, let's call it B. Energy per unit volume in the magnetic field of an electromagnetic wave. So the electric field and magnetic field of an electromagnetic wave carries exactly the same energy. All I have done is I have said, can you guys even see what's going on here? All I have done here is I've said this thing 1 over C square times mu 0 is epsilon 0 from this. Right? Any questions, folks? Anybody? Please. It carries exactly the same electric field of an electromagnetic wave and the magnetic field of an electromagnetic wave carry exactly the same amount of energy in a unit volume. Any other questions? Okay, so we are now done with these general properties of electromagnetic wave. And you know, since we know that visible light, the light that we can see, is a particular example of electromagnetic wave, now let's start focusing on visible light. The properties of visible light, for example, reflection of light, refraction of light, polarization of light, interference of light, diffraction of light, these things will apply to other electromagnetic waves as well. For example, ultraviolet, X-rays, or microwave, etc. So the thing is, but we will just focus more on light, the visible light, the light that we can see. Is that making sense? Okay, let me first talk about polarization. What is the meaning of the word polarization? Have you heard the word polarization before? What does it mean? Okay, let me show you a picture, and maybe that will make it clear what polarization might mean. Okay. So here is the thing. Polarization, it turns out, is a property of any transverse wave, not just electromagnetic wave. By the way, why is electromagnetic wave transverse? Do you know the meaning of transverse waves? In transverse waves, the direction in which the particles of the medium move up and down is perpendicular to the direction in which the wave is moving. In the case of electromagnetic wave, we are just saying that the electric field and magnetic field, they are of course not particles of the medium, but that's what the wave is consisting of, the electric field and magnetic field, and they oscillate perpendicular to the direction in which the wave is moving. That's why electromagnetic wave is a transverse wave. Okay? Now, wave on a string, is that a transverse wave? Yes, it is, because you see the waves, the particles of the medium go up and down while the wave moves forward, right? Sound wave? No, longitudinal, because the particles of the medium, the air molecules here, are going back and forth and hitting the next one and hitting the next one, hitting the next one. So the direction in which the wave is moving is the same as the direction in which the particles of the medium are vibrating. So that's not going to show. So sound wave is not going to show polarization. Let me explain, for example, what polarization means. So think about wave on a string. I'm not even talking about light wave right now, wave on a string. Suppose you were holding the string on one end, I was holding it at the other end, and we put it through a slit like this, okay? And then we said, okay, Michael, why don't you jiggle it in the direction in which the slit is, and you do that, and the wave goes through. Wouldn't the wave go through if he's jiggling it in the direction in which the slit is? It will, right? Because he's not impeding the motion of the particles of the medium. They are able to vibrate the way they were. On the other hand, if somebody is holding the slit this way and he starts vibrating it up and down again, perpendicular to the direction in which the slit is, do you see that the particles of the medium are not able to vibrate beyond this point, and hence the wave is not going to come to me on this side. It will get obstructed by this. Do you see? And this is the phenomenon of polarization, the fact that there is a preferred direction for these things. The particles of the medium are vibrating in a preferred direction. So if you want, you can block a wave by doing something to it. For example, in this case, you put an obstruction that is perpendicular to the direction which the particles of the medium were vibrating, and the wave is unable to go through. No wave comes out on my side when he's jiggling it. In this case, he was jiggling it in the same direction which the particles of the medium were vibrating. The wave is able to go through. This phenomenon of polarization is only associated with transverse waves, as we can see. Because in the longitudinal wave, everything will be like this. The whole thing will go through regardless, right, of whether the slit is this way or that way. So now, what is this phenomenon of polarization in the case of electromagnetic wave? Let me show you first a demonstration. Because again, in the case of light waves, for example, this overhead projector here is giving out some light, right? This is giving out some light. This is almost like that slit that I showed you, but for the case of light wave, this thing is called a Polaroid or a polarizer. It has different names. So the thing is, what does this polarizer do? It turns out this is made of some particular type of molecules. They are called polymers. They are long chain molecules, and they are stretched in a certain direction here, okay? This thing is such that when the light wave passes through it, it only lets light wave pass through which is in that direction in which these things are stretched, for example, and it might absorb the light, say, perpendicular to it. The point is, there is a preferred direction in which it lets light. So And what do I mean by lets light through? When the electric field of the light is in a preferred direction, then it will let the light through. If the electric field is not in that preferred direction, it will get blocked. And that preferred direction we are going to call the transmission axis, okay, or the polarizing axis of a polarizer or a Polaroid. Does that make sense? So the direction in which the light will get through, the electric, if the electric field of light is like this, if the electric field was only like this, the whole light will go through. If the electric field of light is perpendicular to it, no light will go through. That's what the deal is. Now, if this light that is coming out of this bulb here underneath, which is a, you know, this kind of light is called unpolarized light. You know what unpolarized light would be? In which the electric field of the light that comes out can be in any direction, any random direction. Like these kinds of light sources are not giving out light which always has electric field in a preferred direction. So some electric field could be this way, some electric field could be that way. The only thing that you know is that if the electric field is this way, then the magnetic field will be perpendicular to it and the direction of propagation will be perpendicular to it. That's the only thing you know. But it's possible that another light wave will have its electric field this way, another this way, etc. And then the magnetic field will become perpendicular to it and perpendicular to the direction of propagation. But unpolarized light means there is no restriction on the direction of electric field. What do you think will happen if unpolarized light passes through a polarizer, regardless of which way I put the transmission axis or which way I put this polarizing axis or transmission axis? What do you think will happen? Do you think it will change the intensity of light? It will. In fact, regardless of which way I orient it, the intensity of light that will come out, that you will see over there, will always become half after going through a polarizer. So unpolarized light will always get polarized with intensity of light getting slashed into half when it goes through a polarizer. Why is that? Look, and look, let me rotate this thing. Does it matter which way I'm rotating? No. Do you see that the intensity stays the same? And the intensity has become half of what it was before I put that polarizer. Why would that be? Let's think about it. You know, it's not a very hi-fi concept. It's a very easy thing to understand. Think about it this way. You know, when the electric field of light, which is randomly polarized or unpolarized, is in all sorts of direction, you know, you can say, okay, now I'm going to break up all of those electric fields into a component that is parallel to the transmission axis of this, that will go through, and a component that is perpendicular to it, that will not go through, that will get absorbed. Do you see that if things are completely, if the electric field is in all sorts of direction and it's completely random, when you take the component of that electric field parallel to the transmission axis and perpendicular to the transmission axis, half of the electric field will be parallel and half of it will be perpendicular, isn't it? And so that means all the components parallel to it will pass through, all the components perpendicular to it will get blocked, and so the intensity will be half. Is that making sense? Any questions about this? Does that make sense? So basically what we are saying then is this, that whenever unpolarized light passes through any polarizer, you know, outgoing intensity is equal to half of the ingoing intensity. And as I said, let's think about, you know, unpolarized light coming in, whose electric field in all sorts of random direction. This picture here shows you the direction of oscillation of electric field. This is unpolarized light. And let's say it goes through a polarizer or polaroid. Let's say that this has its transmission axis like this. That means this is the direction in which it will let light through. So first of all, the light that comes out of this polarizer, which way will it be polarized? Will the outgoing light have its electric field like this? It will, right? This is another thing, that outgoing light's electric field will always be in the direction of the polarizing axis of the polarizer right before it, if it's not zero. So in this case, this is the outgoing light, and if suppose the intensity here was I0, this is the incoming intensity, I claim that the outgoing intensity is I0 over 2. So I out will be I0 over 2. So if for example, if this was say 1 watt per meter square, that will become half watt per meter square. Why is that? Because as I said to you, if you think about breaking this electric field into components parallel to this and perpendicular to this, all this electric field can be broken up into this component and this component. This can be broken up into this component and this component. And if you do this, half of the electric field is vertical, half of the electric field is horizontal. All the vertical ones will pass through this, and the intensity will be half. Please. Like this? Well, I mean, the only thing is that this light is really not passing through the polarizer then, right? So the thing is, I mean, you now have some light here that's going straight through, that's not polarized at all. But the ones that pass through the polarizer, will still be, the point is that the light that is passing through the polarizer will definitely be polarized, right? Does it make sense? Okay, now, now what do you think will happen if now I actually put another polarizer here? Can you make a guess about what will happen if I put another polarizer here? Anybody? So the question is, suppose I put another polarizer here, and I'm going to do something tricky. Suppose I put its polarizing axis like this, perpendicular to the polarizing axis of the incoming light. What do you think will happen? What is the intensity of the light that comes out here? Huh? Yeah, it turns out that the intensity of outgoing light in this case will be 0. Why? Because this light here has its electric field only oscillating like this, because it's already polarized light, right? This was unpolarized light, but this is already polarized with its electric field pointing this way. And so now if it passes through some polarizer whose transmission axis is like this, then there is no component of this electric field along this direction. Do you see that this electric field is perpendicular to this polarizing axis? So there's no component of electric field in that direction, and the outgoing light here will be 0, no outgoing light. So outgoing light, intensity of outgoing light will be 0 in this case. Let me try to show you that that is the case. In fact, I'm going to now take another polarizer here, okay, and we will see what happens. By the way, do you see that it depends upon the polarizing axis? So in fact, do you see here there's no light coming out? Do you see that there's nothing coming out? Yeah? Okay. So the point is that on the other hand, what would happen if this thing had its transmission axis in the same direction as this one? Any thoughts? Huh? Do you see that it's, yeah, she's absolutely right. In this case, the intensity of the light that comes out here, first of all, the light will have exactly the same direction of polarization. Electric field will be like this, up and down, and intensity will stay I0 over 2, because all of this light will go through. Do you see? And in fact, I think when I was rotating, did you take note of the fact that there was a point when it seemed like, see here it's looking like the two polarizers are crossed or perpendicular to each other, but there is a point like this here. It doesn't even matter that I have both, right? Because the two polarizing axes are parallel to each other, in which all of the light is going through the second one anyway, right? In all intermediate places, it's somewhere in between. And basically, what happens to a polarized light when it goes through another polarizer is given by Malice's law. So this particular law is called Malice's law. So Malice's law, and Malice's law says that if polarized light is sent through another polarizer, I out will be equal to I in times cosine square theta. Now where is it that this cosine square theta comes from? You know, like that theta is the angle. What is theta? Theta is the angle between the direction of polarization of the incoming light and the direction of the transmission axis here. So for example, if I put this thing, if this thing was like this, you know, the angle theta will be the angle that this transmission axis is making with the electric field of the incoming light. Okay? So what we are saying is that this, in this case, this will be theta. Do you see? This is the incoming light, which is already polarized like this with electric field in this direction. This is the transmission axis. This is the angle theta. And what I claim is that the intensity here will be I in. In this case, I in is already I0 over 2. So this is the I in times cosine square theta. Okay? By the way, you can see here if theta was equal to 0, you know, that means this thing was also parallel to this transmission axis. Do you see cosine square 0 is 1. So all the light will go through, that is coming in. If this theta was 90, do you see cosine 90 is 0. So in the case where two polarizers are crossed, nothing will get through. And in all the intermediate cases, you have to figure out what is cosine square theta to figure out how much of the light will go through. What is the intensity of the outgoing light? Why is it cosine square theta? The reason it's cosine square theta is because, remember, the energy of the light, you know, energy density of the electric field is what? We just now talked about it. It's half epsilon 0 electric field squared. Right? It depends upon intensity, will depend upon energy per unit volume, and hence intensity. Intensity is energy per unit area per unit time. So intensity will depend upon electric field squared. And that's why it doesn't depend upon, you know, for example, you might say, oh, shouldn't it just depend upon E cosine theta because electric field component along this direction is E cosine theta? Yeah, it is dependent on E cosine theta, but then you square the whole thing. And that's how you get cosine square theta, and E gets absorbed in this E0 over 2. I mean, in that case, E0 over 2, because we started out with E0, we went through this. So whatever is incoming times cosine square theta. Is that making sense, folks? Any questions about this? You know, there's something that very bizarre that we can do. For example, here is one polarizer. I already showed you. Here's another polarizer. Let's put them perpendicular to each other so that no light goes through. You know, something like this. What do you think will happen if I let a third polarizer in the middle? Suppose I put a third polarizer, you know, somewhere. So in this particular case, it's not like this. So I have the two polarizers be perpendicular so that nothing was coming through here. What do you think will happen if right over here I put a third polarizer with its transmission axis somewhere in the middle? Do you think anything will happen? How many people think that something will go through? So the point is, this is like this. This has its transmission axis vertical. This has its transmission axis horizontal. No light is going through, as you can see here. And now I am going to put one polarizer in the middle of these two, which has a transmission axis somewhere in the middle. The question is, will anything go through? How many people think something will go through? Okay, half the class. It turns out it will go through. Let's see. So all I'll do is I'll put this in the middle. Maybe it's harder to see. Let me turn off the light just to convince you that actually something will go through. Okay, so let's make it as dark as we can. Okay, this is the darkest maybe. See, do you see that, again, it changes, but the thing is there are angles at which light is going through. Do you see that? Is that magic? No, it's not magic, obviously. The job of science is to demystify things, so it's not magic, obviously. So the thing is, why is it that it happens? Well, let's try to understand it based upon what we have already understood. So let's put another third polarizer here, and let's say this has its transmission axis somewhat like this. Okay, the question is, what is the light that will come out now? That's what we are trying to figure out. All right, so the thing is, if we are trying to figure out what's going to come out, let's do it slowly. Don't rush through this thing, because if you go slowly, there's no way you are going to make mistakes. These things are not difficult at all. So who wants to tell me what will be we said that the intensity of light here, this is unpolarized light, goes through the polarizer. What becomes the intensity here? Who wants to tell me what is the intensity here? Is it I0 over 2? Yeah, so that is always true. Here the intensity will be I0 over 2. Is the electric field like this? Since this polarizer has its electric field pointing this way? Yes. Okay, now what do you think? Let's say that the angle between this electric field and this thing is, let's say, 60 degrees. Who wants to tell me, first of all, what is the direction of electric field of the light that comes out here? Go ahead, please. What will be the direction? Very good. The direction of electric field, it's always going to be the component of this electric field along the direction of transmission axis, right? Component of this along this direction is always going to be in the direction of this thing. So this will be the direction. These pictures are getting too close. Let me just move it a little bit. So do you see that the direction of electric field of the outgoing light will be like this? And the question is, by the way, this is the transmission axis. What will be the intensity of this light? Tell me. The incoming intensity was I0 over 2. It will be I0 over 2 times what? Yeah, it's E cosine theta, but we have to take cosine square. That's what Maxwell's law says, because the intensity is energy per unit area per unit time, and energy goes as electric field squared. That's why it's cosine square theta, not just the component of electric field, not cosine theta, but cosine square theta. So is everybody agreeing that this is the intensity of this light? Now, does this light have any non-zero component along this horizontal direction now? It does. What is the component? What would be the angle between this electric field and this horizontal direction? Isn't it 30 degrees if this was 60? It is, right? So what would be the outgoing light here then? First of all, what would be the direction of outgoing light? Should that be this along the direction of the transmission axis? Yes, outgoing light will always be in the direction of the transmission axis of the last polarizer. And now we have to find the component of this electric field along this direction. Do you see it's going to be E times cosine 30? And we have to take square of that. So it will be whatever is the incoming intensity times cosine square 30. Right? That's what Maxwell's law says. Do you understand what I'm saying? So it will be incoming intensity, which is I0 over 2 cosine square 60 times, this is the incoming intensity, times cosine square 30. Right? So you can see that the light will go through. And how much light? Suppose, I mean, I'll let you do the math, but the thing is, suppose the incoming intensity was 1 watt per meter square. You can put 1 watt per meter square here, and you can do a cosine square 60, cosine square 30 divided by 2, and you can figure out how much should be the outgoing intensity. But it's definitely non-zero, right? In fact, do you see that if we put a lot of polarizer here, one after the other, and they had their polarizing axis only slightly off, a lot of light could go through. Do you see what I'm saying? I mean, you can have a stack of polarizers. You know, one starts vertical, then the next one slightly off, slightly off, slightly off, slightly off, slightly off, and the final one will be horizontal. In that case, the transmission could be almost, close to 1 if you close them enough, because cosine of, say, 2 degrees or 5 degrees is almost 1. Do you understand what I'm saying? And I always use this analogy to say to people that even if you started out not knowing something, don't think that there is no hope. Learn, slowly learn. So it's not like, oh my gosh, the material in that course is like perpendicular to my knowledge state. So nothing is getting through, because the point is that, you know, you have to just slowly build on your knowledge, right? And slowly, if you build on it, in the end, you will get to where you want to be. And again, you know, it depends upon teaching and learning both. But I think this analogy is a good one to think about. Any questions here, folks? All right, then we are done with polarization of light. I just want to quickly start doing reflection and refraction. In reflection of light, I'm not going to say anything, basically. All I want to show you is that when light falls on any surface, part of the light gets reflected, right? The shinier the surface, for example, if you use a silver surface or a mirror or something, a lot of light will get reflected. The only thing that I wanted to say about this is that if you have this, say, for example, mirror surface here, you have some light that is incident at some angle to the perpendicular or normal, and let's say that this is the angle of incidence, theta so phi, then the direction in which light will get reflected will be such that this angle of reflection with respect to the normal is going to be exactly equal to the angle of incidence. So the law of reflection says that angle of incidence and angle of reflection are going to be equal. Okay, any questions about this? Anybody? Okay, I am not going to talk very much about reflection of light. Maybe just one more thing I wanted to say, which is that, do you think that, you know, when you look at yourself in the mirror, do you think that the light really arrives on the other side where your image is formed? No. The image that you see is what is called a virtual image, you know, because really, I mean, when are you able to see something? You are able to see something when the light from that object is able to hit the retina of your eye. So I'm able to see him and him just because the light from there is coming to my eyes. If the light from some object is not coming to my eyes, I will not be able to see that object. Okay? So that's the idea. You always have to think about, why am I able to see something? Because there must be some light from some object that is hitting your retina, and then you see, oh, this thing is there. Now in this particular, here, suppose this is your mirror, right? And that is our eye over there. The question is, will I be able to see the chess piece or not? And the answer is yes, I will be able to, because if the light from the chess piece here goes and reflects such that the angle of incidence is equal to angle of reflection, my eyes have this ability to, even though I'm not directly seeing this thing, I am seeing this light that is reflected from this thing. And what I do is my eyes have the ability to extrapolate this ray of light, and it seems to our eyes that the object is actually located there behind the mirror. So next time you look at yourself in the mirror, it will seem like to you that you are behind the mirror at the same distance. You know, your image is behind the mirror exactly the same distance as you are in front of the mirror. Is that making sense? So if I move further away, you will see that your image will move further away in the mirror at the same distance away. Right? Okay, refraction of light is something we'll talk about next time. Have a great day, folks.
Professor Singh is a lecturer in the physics department at the University of Pittsburgh. For more information about Professor Singh and her research, visit her website in the description below.